Delta is one of the first-order options Greeks and is a vital component of options trading. In today's video, we're going to be discussing the meaning of options delta and how it is calculated. We will also learn the exact derivation and why what you thought of as delta might not actually be the right answer. Let's dive in. At a high level, delta is a derivative of the option price. Specifically, it is the first derivative of an option price with respect to the underlying asset's price. For example, a delta of 0.5 means that for every dollar change in the underlying asset's price, the option's price will change by 50 cents. A higher delta indicates a higher sensitivity to the underlying asset's price, while a lower delta indicates a lower sensitivity to the underlying asset's price. Delta values exist between 0 and the number 1. Delta values of 1 indicate that the option's price is moving in lockstep with changes in the price of the underlying asset. But now you might be wondering, how is this number calculated? The easiest way to calculate delta is to simply look at the Black-Scholes formula. If you're familiar with the Black-Scholes formula, then you know that the term ND1 for a call option is equal to your delta. If you're curious about the Black-Scholes model and want to learn more, we invite you to look at our video diving into the calculation of this famous financial formula, linked in the description below. But we don't think that this is a very sufficient answer. If delta is the first order derivative of the option's price with respect to the price of the underlying, why is it that ND1 is the answer? Also, is ND1 actually the correct answer? For this proof, we're going to need to use a little calculus. Coming from someone who enjoys linear algebra far more than he enjoys calculus, this video was less than fun to put together. That is your hint to like and subscribe. If we take our Black-Scholes formula for a call option, given as the following, C equals the current underlying's price times ND1 minus our strike price discounted times ND2, we must now find the solution for dC ds, which is our delta. Therefore, we know that the delta equals the partial derivative of C with respect to S, which looks like this. Now we can break this down into two parts, which will be much easier. First, we will differentiate our S in D1 value, and then we will move on and differentiate our discounted K to the negative RT in D2 value. First, let's examine the reward portion of the Black-Scholes formula and derive this with respect to S. To derive this portion, we need to use the product rule. As a refresher, the product rule states that d dx of two functions, u and v, for this the solution is u prime of x times v of x plus u of x times v prime of x. If we assign each of these components a value based on our equation, we see that the product will help simplify our derivative to the following. But we're still left with the d in d1 over ds value. We now need to derive this portion. Here we will use the chain rule. Again, as a refresher, the chain rule states that for a function d dx, for v of g of x, the derivative equals v prime of g of x times g prime of x. This simplifies our d in d1 over ds value to the following. For those wondering, the n prime d1 value is simply the probability density function, which is given by the following. For simplicity's sake, we're just going to be referring to this value as n prime d1. But if you wanted to calculate the formula for yourself, this is the function you would sub in. Now we are left with our final d d1 ds. This is the last step in deriving the first part of our Black-Scholes formula. Fortunately, this derivation is more simple than you might realize, as most terms involved are constants. If we sub in the full formula for d1 from the Black-Scholes model, we get this beastly equation. The key is to isolate all terms that depend on s. When we realize that this entire section of the equation is nothing but constants, we can remove them, as their derivatives are 0. This leaves us with the derivative of the log normal of s with respect to ds, which simplifies to 1 over s. Putting this back into our dd1 ds, we find that the piece simplifies to 1 over s times sigma times the square root of t. Now we can plug this piece back into our d in d1 ds. With some simplification, we find that this component equals n prime d1 over s sigma root t. Taking that, we can then plug it back into our ds in d1 ds equation and find that the entire thing simplifies down to n d1 plus n prime d1 over sigma root t. This solves the first part of our Black-Scholes derivation. Now, onto the cost portion of the Black-Scholes. Like we initially did, by utilizing the product rule, we can see that our value simplifies out relatively nicely. We are, however, still left with a d in d2 ds value. So will we do everything we just did all over again? No way. Why? Because we know that d2 equals d1 minus sigma root t. Sigma root t is a constant, and it derives to 0. Therefore, d in d2 ds is equal to d in d1 ds. So our cost portion of the Black-Scholes formula derives neatly down to ke to the negative rt times n prime d2 over s sigma root t. Plugging this equation back into our first section, we find that the completed derivation for the option price with respect to changes in the underlying price is as follows. But hold on, what's this equation? Didn't we already say that delta is equal to just the first part, in d1? What's the rest of the equation? Do these terms secretly cancel out and we're left with just in d1? The answer is no, not really, but these terms are incredibly small. So small, in fact, that they are virtually zero. Don't believe us? Well, we didn't believe the math either. So we set up a test in Excel and found only one example of the delta values not equaling out. There are certainly other examples of this, but it turns out if you set S equal to K, volatility at 30%, interest rates at 1%, and time equal to 2 years, you will actually see a difference in delta. You will need to go out 15 decimal places before you see the deviation, but it's there nonetheless. Needless to say, ND1, for all intents and purposes, is delta, and there is no need to calculate out the entire equation. If anything, it probably costs more to compute than the value you'd extract from getting the exact number. When we graph delta, we see that the following happens to the option price with respect to changes in the underlying price while holding all else equal. If we change variables like time, volatility, or interest rates, we see that the way delta acts changes with respect to these variables. However, delta is always bound between 0 and 1. Essentially, what we're doing is squashing or stretching the distribution as we change the variables associated with ND1. We hope you enjoyed today's video, and we would love a like and subscribe if you're interested in more content like this. Now please, enjoy one of our other great videos on topics in finance on screen now.